All right, we're up.
Okay. Hi, everyone, and thanks for tuning in to this week's Quantum Chaos seminar. So this week, it's my pleasure to introduce our speaker, Annabelle Bohrdt. So Annabelle is doing her PhD at Technical University of Munich. She's also affiliated with the Munich Center for Quantum Science and Technology. During her PhD, she also did an extended exchange with Harvard University in the US. So she's done a lot of really interesting research on quantum dynamics, always in close connection with the experiment. And today she will be talking about probing dynamics in quantum simulators. Take it away, Annabelle.
Hey, yeah. So I'm Annabelle, and I'm really excited to be here today and talk a bit about my research. And I also want to take the opportunity to thank the organizers a lot for having me and also for organizing this nice series. So I have here a very broad title, Probing Dynamics in Quantum Simulators. And I want to focus on two pieces of work that I did with Christian Mendel, Manuel Endres, and Michael Knapp, and then also Michael Knapp and Ben Kiao and Pedram Rushan at Google. So, okay. As I said, it's a very broad title. Yeah, quantum simulators give us a huge opportunity to probe actual dynamics, in particular non-equilibrium dynamics of isolated or almost isolated quantum many-body systems. And under this title, I could be talking about almost anything. So for example, dynamics can be observed with cold atoms in quantum Gauss microscopes. So for example, this here, they prepared a spin spiral and then observed what happens to it during the dynamics. Or for example, here they looked at an array of Rydberg atoms, prepared it in some state, they did a quench and looked at the dynamics. There are many other platforms, for example, trapped ions and so on. Okay, so let's see what we're going to do today. I want to start with some a bit older work about the spreading of quantum information in the context of out-of-time ordered correlation functions, and also about thermalization, and then also about the breakdown of thermalization once we add disorder in the case of many-body localization, and what we observed there experimentally with the Google team. Okay, so let's get started. So in classical chaos, we basically look at, the standard example is this butterfly effect, where we look at the sensitivity on the initial conditions. So basically we say we change the initial conditions slightly, and over a long course of time, we get an exponential deviation in the outcomes. The thing is now that quantum evolution is unitary, so it's kind of hard to define the same thing. However, we can consider this correlation function here, which is basically the absolute value squared of the commutator between two operators at different times. And this is motivated, so if we look at, for example, choose particular Q and P, so location and momentum, then in a semi-classical picture, we kind of can relate this to our classical chaos picture. So this is kind of a very hand-wavy motivation for this. Okay, so if we now look at our correlation function and write all these terms out, we can rewrite it in form of this correlation function. And here it comes into play why I said out of time ordered correlation function, because as opposed to a time ordered correlation function where we would just have V of 0, W of t or something like that, we go back and forth in time. So basically we have to somehow change the evolution of time in the middle of the thing. Okay, so what has this to do with anything? Okay, so let's take an example, for example, of a spin chain, and we start from two initial pure states, which have nothing in common but that they have roughly the same average energy, but opposite expectation values for some local non-conserved operator, for example, SC on some side. Okay, if we now have a chaotic system and we look at sufficiently long times and the system thermalizes, the expectation value of that operator, say SC on a given site, will approximately be the same in both time-evolved states. So if we only look at operators like this or observables like this, we will not be able to see from which initial state we started, and all this information has been lost. Okay. Now maybe one step further would be to look at entanglement. So if we consider one spin, say A, in a chain of spins, which is initially entangled with some reference spin outside of the chain, which we can place in a box, then during the time evolution of the quantum system of the spin chain, the spin A will entangle itself with the remainder of the system. So therefore, at long times, if we want to recover the entanglement with the reference spin, we need to have access to more and more degrees of freedom. And it's not sufficient anymore to just consider spin A. And in both of these examples, what happens is that the information gets scrambled and in a way spreads over all of the degrees of freedom in our system. Okay, so now let's go back to our out of time ordered correlation function. If you write our operator W of t in the Heisenberg picture, we see that it basically can be written like this. And even if now this operator W is local initially, say it's something like SEZ or like whatever you want, once you come to a certain point in time, it will have spread over many sites. So basically, this W of t is no longer local. And the out of time ordered correlation function is now just a way to probe how non-local this operator is, or how far it has spread throughout a system. And therefore, we look at the squared commutator between this W of t with some other operator, preferably, obviously, some other more or less local operator at a different site. Okay, and so initially when we start and we are at time 0, this commutator will be 0 because it's just two independent local operators which will commute. But once W has spread to the location of V, this will become significantly different from 0. Okay, so what we looked at now is the one-dimensional Bose-Hubbard model. So you basically have bosons which sit in a lattice and they hop from side to side and they interact with interaction strength U. And here we consider a finite temperature ensemble. And this is now numerics done with matrix product operators. And what you see here is first the normal time-ordered Green's function. And here, the out-of-time-ordered correlation, where we choose as our operators W, Cj, and V is Ci. So it's really just the creation and annihilation operators at two different sites. And in this case here, we are at comparably low temperatures, or like reasonable temperatures. So you still see something happening in the Green's function. You see something like a spreading out. And in the out-of-time ordered correlation function, you see a really nice light cone. And this light cone really corresponds to the spreading of information throughout the entire system. Okay, so far, it feels like these are pretty much the same. But if we now go to much higher temperatures, we come to an incoherent regime where this Green's function, this time-ordered Green's function, decays very fast in time. So we basically, at some later time, we don't get any signal at all. So if you go to larger distances or longer times, this thing is just 0. However, the out-of-time ordered correlation function still shows the same light cone that we saw before. So even though we don't really have well-defined quasi-particles because their lifetime is just so short, we still see this nice light cone spreading. Okay, so this was so far very theoretical. So now how can we probe this? And to probe this, one tool that we want to use in our proposal is this beam splitter operation, which has, for example, been realized in Markus Greiner's group. So they have a quantum-wise microscope and they prepared 2 copies of the system. So here you really see the atoms sitting in the system. In this case, they only looked at a 1/4 system. So these are the 4 sides of your system, and you prepare 2 copies of this system. And now you can, in this direction, the y direction, you can lower your lattice and let your atoms tunnel between the sides in y direction, which enables this beam splitter operation. And we will get back to why this is useful later. But you can see that really, if you start from 2 atoms, each in its own side, and you have this beam splitter operation, after 1/8, you really get this superposition. So you really realize this 50-50 beam splitter. Okay, so what we want to do now is we also prepare 2 copies of the system, and then we create a hole in the left copy. So we get our Ci, we let the system time evolve, then we create a hole in the right copy, now at a different side because you want to look at side I and J. And then we perform this beam splitter operation And so before the beam splitter operation, the state that we have reached is this here. So as I said, we have our state psi, we create a hole, time evolve, or we time evolve, create a hole. And now if we measure the swap operator, and this is really what this beam splitter operation does. So if we let this beam splitter happen, we really can swap the occupation between the two sides. So we really can exchange the two systems. And the measurement then is just measuring the parity of the atoms in the outcome. So this is a very nice and easy measurement to do in a quantum gas microscope. And if we do that, we exactly get out the absolute value of our Green's function. Okay, now we can take this one step further and also look at the out of time ordered correlation function. In this case, the protocol is almost the same. So we do this 2-point sequence. So this is everything that's in the blue box above. And then we have to flip the sign of the Hamiltonian. And this is really what the out of time ordered correlation function is about, that you reverse the sign of your Hamiltonian, or your time evolution, and see how much you get back to your original state. And then we repeat the 2-point sequence, and afterwards perform this beam splitter and parity measurement. So we measure the swap operator. And this way we can really, with tools that are, all of which are accessible in current experiments, we can measure this out of time ordered correlation function. And now I should say this topic has really interested a lot of people. And over time, there has been a lot of proposals. So this is really just a small selection of theory proposals, how to experimentally access these out of time ordered correlation functions and thereby probe the scrambling of quantum information. And I should also say that in the past, I think 3 or 4 years, there has been a couple of experimental realizations. So these are the experiments that have been performed, most of them on trapped ions or nuclear spin chains, where they were really able to measure these out of time ordered correlation functions. Okay, so we saw that even though we are at high temperatures, we still get this ballistic spreading of quantum information. And in the beginning, I explained how this spreading of quantum information and this basically this loss of information about initial state comes with the thermalization of the system. However, if we have if you have conserved quantities in our system, then there might be things which thermalize slower. So in this particular case that we're considering, the global density is conserved. So we have a fixed number of particles in our system. And kind of the reason we thought about this in the first place was that we thought, okay, if we take this out of time ordered correlation function and time order it, we just get a density correlation function. So the question that we had was, well, do we actually see anything in this out of time ordered correlation function that we wouldn't see in, if not in the Green's function, then in this density correlation function? However, we have density conservation. So this gives us basically, how the density changes over time and space must zero out. And now if you're in a hydrodynamic regime, we can use these phenomenological equations like Fick's law and obtain a diffusion equation, which in the end means that we get diffusion, as you might have expected. Which means that if we look at these density correlation functions over at high temperatures at least, we get this diffusive behavior. So here you see this, the same side density correlation function as a function of time goes with square root of t. At lower temperatures, you still see this ballistic behavior, but if you were able to go to sufficiently long times and big systems, you would also obtain this diffusive behavior. So you would enter this hydrodynamic regime. And what this means is that at these high temperatures, where we saw the ballistic spreading of the light cone, we have diffusive behavior of our density correlation functions, which means that it takes like system size squared for these density correlations to thermalize, while our quantum information is already scrambled throughout the entire system. So therefore, the actual thermalization of the system is much slower than the spreading of quantum information. Okay, so this is slow, but it happens at least. If we now add this order to the system, we can get to a case which is called many-body localization. And in this phase, there is no thermalization, but the system is just stuck. So basically, in a way, we have an extensive set of conserved quantities which inhibit this thermalization. Okay, so we still consider the Bose-Hubbard model. So we still have this hopping of particles, we have this interaction U, but we also have a disorder potential W here now. Okay, so what does happen in this many-body localized phase? Well, first of all, as the name says, you get localization. And this is something that has been observed, for example, in quantum-wise microscopes. So these are two examples from Iman and Bloch's group in 1D. So they prepare a charge density wave where you have like occupied, empty, and so on. And as they increase the disorder strength, this pattern of this charge density wave remains stable over time. And now here on the right, they have a 2D system. So they prepare, so this entire picture would be their system, but they prepare their atoms only in the left half. So this link on the left-hand side is a single shot, and on the right-hand side is an average over many, many shots. And you see that even after very long times, you still have an imbalance between left and right half of the region of interest. So you still have way more atoms on the left than on the right. So they don't really thermalize to the right-hand side. Okay, and so now we looked at this with the team of John Martinez at Google in a superconducting qubit setup. And so there, the first problem is also, do the particles localize? And so what we did here, for example, is to start with 2 excitations in the system. So it's a 1D chain of 9 sites, and there are 2 particles in there. And now we tune the disorder strength. So dark blue is a very high disorder strength, red is a very low disorder strength. And you can see that as you increase the disorder strength, you more or less stay at the same particle number. So this is looking at the population of one of the 2 sites where a particle was initialized. And you see that after some initial hop, which leads to a small decay, you basically stay constant if you're at sufficiently high disorder. And we can now at this time, so basically at late times, we get some interactions with the environment and some decoherence. So we basically do not trust it at very long times. But if we look at a long time already and compare different disorder strengths now, we see that if we go to low disorder, we reach the thermal expectation value in the sense that if we prepare, for example, the blue line here is 1 particle on 9 sites, then we reach 1 particle on 9 sites, and so on. If we prepare 3, we reach 3. And as we increase the disorder strength, the particle number on the site which we initialized it on gets closer and closer to 1. Okay. But so far, this is not very exciting because it's just looking at particles that don't move. So there is kind of a very nice description of why we still should be excited about this many-body localized phase. And the idea is now that we can connect the eigenstates of this many-body localized Hamiltonian to product states by a finite number of quasi-local unitary transformations. So basically, we go to this taus instead of the SIZs. And I should mention that in the limit where we are operating, we kind of can consider our system more or less as a XXZ spin chain because we have very low occupations and our interactions are strong enough. Okay. So basically, we know that these taus now commute with the Hamiltonian because that's really how we constructed them. And we also know that since all these U's, so this is what's displayed here, are quasi-local, these taus have a strong, so tau I on set I has a strong overlap with sigma IZ, or SIZ, which means that even though there might be contributions from other sites, it decays very quickly with distance. Okay, and so knowing that these operators commute with the Hamiltonian, we also know that there can't be any tau I, X, or Y in the Hamiltonian because they don't commute with tau IZ, So if they appeared in the Hamiltonian, this wouldn't hold. But this means, on the other hand, that we can expand our Hamiltonian in this form. So we know that this tau bit Hamiltonian can be written just as a sum of a local field and then interactions between tau z's, tau z's. And these couplings also have to decay exponentially with distance. And the nice thing about this is now that basically everything is just dephasing, but there is no actual, so the tau z's themselves cannot change because there are no tau x or tau y terms in the Hamiltonian. And so from this picture, it's very easy to understand a lot of dynamical features. Okay, so for example, now we looked earlier at these out-of-time autocorrelation functions, and one point of them was to reverse the sign of the Hamiltonian. And in a way, something similar is what's been done in these echo experiments. So basically, okay, so this is just the Hamiltonian that we want to look at. And if we now look at the spin echo, it consists of bringing your spin in a superposition. Then after time evolve, after some time evolution, apply a pi pulse, which means to turn the spin around. Then time evolve again for the same time and apply a pi/2 pulse again. And the way I actually learned this during undergrad was that you can imagine that you have a group of kindergarten children and they are slightly different ages, slightly different fasts, but they want to have a race. And so what you do is you let them start racing and they all go as fast as possible. Then at some point you clap and they have to turn around and run back. And therefore you, by this, you choose the distance for each of them individually. And this is kind of the very hand-wavy picture for this. Okay, so basically this pi pulse is supposed to turn around all your fields. And in this case, your fields are these delta i's. Okay, so what happens is we start from the superposition after the pi/2 pulse, we time evolve. So we get these phases, which is basically just what's written here in the Hamiltonian. So we just get this plus delta I or minus delta I here. And then we apply the pi pulse, which just means that we switch those guys here. And then we time evolve again, which means that we get rid of these phases, which is basically the kindergartners having the shorter distance to run if they are slower. Okay, if we now in the end apply our pi/2 pulse again and then measure sigma z or tau z in this case, we would just get 1. So this is all nice enough, but we don't really see any interactions. So basically, if we had Anderson localization, which is many body localization without many bodies, so just localization without any interactions, we would get the same result. And now we can slightly modify this to probe those interactions. And the idea how this is done is to apply the same protocol to one spin, but at the time when we apply this pi pulse to this one spin, we apply a pi/2 pulse to some other remote spin. And thereby we probe the interaction between this second spin and the first spin. Okay, so we again start from our state here. Now we time evolve. So far nothing has changed. Now we apply the pi pulse, and then we also apply at this side j, this pi/2 pulse. And now things get way more complicated, but what you already see is that you here now not only have this delta I, but also this delta I tilde. And this delta I tilde is basically this field that we see here, but with this tau j flipped. So the spin on side j has been flipped now. And what this means is that if you now apply your pi/2 pulse in the end again and measure your tau I z, you get something like this. And this way, the difference between those two deltas is exactly the interaction jij between the two tau bits on side I and j. Okay, so what do we expect? When we are not in a localized regime, well, first of all, this tau bit picture doesn't hold, but also we don't have this nice picture where we just have decoherence but no particle motion. So basically, you cannot think about all of this in the way that I explained. You just get a fast decay. Now in this non-interacting localized regime or Anderson localized regime, you basically get the same result in both cases, because whatever you do to your spin or your taubit at site J doesn't really bother the taubit at site I. However, in the MBL regime, you get a difference, because here you get the same thing as before, but here you get this cosine, and in this cosine there is this difference between having the spin on site J up or down. Okay, so this is the first way to probe really the interactions in this many-body localized phase. And the nice thing is now that in the superconducting qubit setup, they can easily apply pulses like this and read out whatever you want to. Okay, so what did we see? On the right-hand side, you see exact diagonalization results. On the left-hand side, you see the experimental result. This is as a function of evolution time, which is here the same timescale. And it says here that we measured purity, which is because we didn't apply this last pi/2 pulse, but instead just measured the purity. And what you see is that you initially get this decay here, which is just your first small hopping event, which usually takes place. But then you get exactly what we expect. So note that the scale here ends at 0.6. So the red curve is just a spin echo, which corresponds to this curve here, which saturates. And then the other curves, depending on the distance, give you the Deer echo. So the side here that's marked here tells you which spin J we did our Deer echo pulse on. And you see that as you get closer and closer, your interactions get stronger and stronger. So you see a stronger and stronger effect here. And this is exactly what also numerics would predict, and also what you would expect from the experiment. Okay, so this is kind of an indirect way to probe the interactions between those taubits. But actually in this setup, we can really probe them directly. And the way this is done is we look at just two spins now. And so the protocol is basically to prepare one of them in the superposition state and the other one either in 0 or in 1, or either down or in up, and then time evolve and measure sigma x on site I. And now, why does this do anything interesting? So we start again from the state, we time evolve it, and we measure sigma 1x. And we just, in the time evolution, the only thing that happens is that, again, as always, that we acquire these phases. And if we now measure the sigma x here, we get this cosine. And in this cosine, we already have our interaction between this J1, 2, between the two spins. But we also have this field H1, which we don't really want. So we repeat the same procedure with the spin on site J down instead of up. And now from the so this is basically the two curves that you can see here, the blue and the red curve correspond to the second spin being down or up. And you can see now that in both cases we get a cosine, and this is real experimental data here. And from difference in their frequencies, we can directly extract the coupling between those two spins in this taubit picture, which is pretty cool. So what comes out is, if you look at, so this is basically a histogram. So if you do this many times and you look at spins which are further and further away, you count how often which Jij occurs, and you see that you actually get pretty broad distributions. And now if we basically look at the average of this, so we look at really as a function of distance, what is the average value of our Jijs, we see that we really get a decay. So basically here you see it, the same data in a half logarithmic plot, and you see that it really more or less decays exponentially. So as you go further away from your reference site, the interactions become smaller and smaller, which is what you would expect. And also, if you increase your disorder strength, so here we double it, we really go from 5 to 10, you get a smaller, a more narrow distribution in this case. So this is really what one had would have expected. Okay, so this is very nice. And I would say when you hear about many-body localization, there are basically two things that you always hear. The one is these taubit picture and these non-local interactions, and the other is the entanglement behavior. And so one way to look at this is, if you start, again, we look at two spins, we do the same thing as always. We just look at two spins. At this time, they start both in a superposition state, and you let them time evolve. Then you trace out the second qubit to get a reduced density matrix of one of your two qubits, and then you get a reduced density matrix like this. And if you now want to maximize your von Neumann entanglement entropy, you want those entries to vanish, which means that you need to your J12 times T to reach something of order 1. And this means that if you now, instead of looking just at two spins, you look at an entire ensemble of spins and you trace out half of your system, you need to wait exponentially long in time till you actually reach that point, simply because those Jijs to your distance sites decay exponentially with distance. And this means that you get this logarithmic growth of entanglement entropy at long times. Okay, and this is now something that has been observed or is quite interesting to study, but it's kind of hard to actually probe entanglement in experiments. So yeah, what you really want to do is, if you have a product state where A and B don't talk to each other, you can trace out B and your part A is still a pure state. But if you have an entangled state and you trace out B, you get a mixed state in A. And this is kind of something that you want to probe. Now, with the beam splitting operation that I introduced earlier, you can probe not directly the von Neumann entropy, but you can probe those Rényi entanglement entropies. And this is something that has been done in the group of Markus Greiner, so in this quantum gas microscope. They have looked at those Rényi entropies. And here, for example, in this case, they go from a Mott insulator to a superfluid. So the scale is very confusing, but U is big here. So you have strong interactions here, small interactions here. And you see that your Rényi entropy, which is kind of a measure for your entanglement in the system, goes up. And here's how your system is split up. So for example, the green curve is for half of your 4-side system, so for 2 sides. And they really observe nicely how this entanglement builds up in the superfluid case. But however, this is not really the entanglement entropy, but just in a way the Rényi entropy, which is for them easy to measure because they just have to measure rho squared, which is exactly what comes out from this beam splitter operation. Now in the same experiment, they can also apply a disorder field so that they get this on-site disorder. And in this case, they still don't really can measure the von Neumann entanglement entropy, but they came up with a clever way. So on the left hand here, you see the thermal case, on the right hand, the MBL case. And they now distinguish between the number entropy, which basically just tells you how likely it is. So if you cut your system in half, how likely the occupation number in half of your system is. So this is also very easy to read out from those experiments. And then also the configurational correlator. And here you actually look at how likely which configuration of atoms in your half system is. And while in the thermal case, so when you have no disorder, you see that both go up very quickly. So basically for the first hopping event, you go up and then saturate. In the MBL case, you see this logarithmic growth really in this configurational correlator. So this is pretty nice, but it's still not quite measuring the entanglement entropy, but just a proxy for it. Now in a superconducting qubit setup, you have the advantage that you can really do state tomography, which means that you can really reconstruct the density matrix. So this is an example of experimental data where we start from, so we here prepare a Bell state between 2 spins, and there is some other particles floating around in the system. And then we reconstruct the density matrix of this 2-side subsystem here. And these 2 cases here are for different disorder strength. So this is 10, disorder being 10J, and this is the disorder being less than J, so 0.5J, so very small. And you see that if you have strong disorder, basically nothing happens and you stay in your Bell state if you look for longer times. But if you have very weak disorder, you basically get dynamics in this density matrix and basically do not remember your initial state. The nice thing is now that from this density matrix, from this 2-qubit density matrix, we can really get different entanglement measures. So the first thing is, as we looked at before, the von Neumann entanglement entropy. So we can really just look at this quantity now. And this is what numerics predicts. So numerics predicts that, okay, there is no legend here, but if you decrease J now, so basically your ratio of disorder strength over hopping gets bigger as you go up here. So you see this nice logarithmic growth here. So for example, this blue curve is really beautiful, showing this logarithmic growth. You should notice that the time scale here is logarithmic. Okay, now if we do this in the experiment, what happens is very nicely, so we only can go to smaller times as we saw before already. So this is now the numerics up to these times that we can go to, just a cutout of the earlier plot. And you see that we get this nice logarithmic growth in the experiment too. So you really see that if you plot your time on a log scale, that you get this straight line here in this plot. The problem is now the black line corresponds to no J. So there is actually no hopping, so nothing should happen. So this should be really zero constant, which is what you see here in the numerics plot. There's just nothing happening. However, in the experiment, we already see this rising, and this is probably due to some experimental imperfections, to coupling to the environment, whatever. So this plot really can only provide us with an upper bound on the entanglement that we have, and it doesn't really give us a fair estimate. But there are different quantities that people have defined in the past to really extract the entanglement that you have in your state in a situation like this. And one of these is the entanglement of formation. So the entanglement of formation basically tells you how much entanglement you would need to produce the observed mixed state density matrix. So we have our density matrix rho, and we want to know how much entanglement would we need with an optimal protocol to get this density matrix. And now the thing is that how this is defined is that you can write your rho as a pure state decomposition, and there are many different ways to do so. And for each pure state, you can of course define your entanglement as before. You can just, get a bipartition of your system and calculate your von Neumann entropy. And now the entanglement of formation of your mixed state is the minimum over all possible pure state decompositions. The problem is now this is really a bit awkward to calculate, because how do you know that you have the minimum here? But luckily for our very special case, there is a solution. So Wujas, they developed a formula really for 2 qubits. So this really saves us. So the motivation is if you define a spin flip operation. So basically this tilde means that you flip your spin. And the way you realize this is by complex conjugation and then applying the Pauli wire matrix. Then if you look at pure states, you can define the concurrence. And this is just the absolute value of the overlap of your original state and the spin flip state. And this thing is itself a measure of entanglement. And the way you can see this is, or like one way you can see that it's not complete nonsense, is to look at an example. For example, a singlet state. So when we have down up minus up down. Now if you spin flip it, you get the same state just with a minus sign. So the overlap of the thing will be 1. On the other hand, if you have a pure state, and for example, one like up down, you flip it, you get down up, then your overlap is just 0. So you see this somehow already measures your entanglement. And now in this paper here, they showed that the actual entanglement, so what we defined before, is given by this function of the concurrence of psi. So the concurrence makes sense. We saw that before, and now we define this kind of ugly function here. And you can look this up in this paper, but you get your actual von Neumann entanglement that we defined above back this way. So now the nice thing is that we can now take this, because we don't have a pure state psi, but we have our mixed state density matrix rho, but we can take the same thing and look at the square roots of the eigenvalues of rho tilde. So the tilde is again the spin flip operation as before. And now we look at those eigenvalues, we define the concurrence, and then our entanglement of formation is just the same function of the same concurrence of rho instead of psi. Okay, so let's go to the experiment and see how entanglement builds up. So what we do is we look at, so these are 3 different setups, but they all show you more or less the same. It's just a 1 by 10, 2 by 5, or 3 by 5. And we look at different subsystems. So the different colors here are whether A looks at its nearest neighbor, next nearest neighbor, or third nearest neighbor. And we look at this entanglement of formation that we defined before as a function of evolution time. And what we see is this grows faster if the qubits are closer to each other. So the nearest neighbor, the brown curve, always has the fastest and highest rise. And this makes sense because the interactions decay, as we saw before. So for example, A and B2 just have less interactions than A and B1. And now if we increase the dimensionality, or if you, basically what we do here is just increase the number of neighbors that a given site has, then a given qubit, for example, A, entangles more with the environmental qubits, so in this case, the up and down here. And therefore, it reduces how much A and B1 or A and B2 can be correlated. Okay, and then at long times, we see this decaying again because the interaction between A and B is outcompeted by the interaction with all the other qubits in our system. Okay, so this is basically the entanglement of formation. So how much entanglement do we need to build this state? Now let's go in the other direction. So if we have a given state, how much entanglement can be distilled? So basically, this quantifies if I have a given density matrix rho, or better even if I have n copies of this state, and I find some optimal protocol only of local operations and classical communication, how much entanglement can I distill? And with this, I mean how much equivalent pure state entanglement can I distill? And this is again a bit awkward as before because, well, I don't know what the optimal protocol would be to distill this entanglement. So I don't really know how to calculate this distillable entanglement, but there are bounds at least on this quantity. So it's basically lower bound by the coherent information. So this is the von Neumann entropy of 1 qubit minus 2 qubits. So for this 1 qubit, we even trace out the second qubit of our subsystem. And it's upper bounded by the logarithmic negativity. And this is basically the partial transpose with respect to one of those 2 qubits. And again, you see that we are really looking at quantities that are luckily for us defined for this case of having 2 qubits. Okay, so what we do now is we prepare a Bell state. So this subsystem AB is now in a state that's maximally entangled, and the rest of our system is just a boring product state. And now the 2 colors that you see here, the blue and the red, are strong disorder versus weak disorder. So in the red case, we are just in the thermalizing phase, whereas in the blue case, we're in the many-body localized case. And now we look at this distinguishable entanglement, or basically its upper and lower bound, as a function of time. And what you see is that if you have sufficiently strong disorder, you really keep this distillable entanglement between those 2 qubits for a very long time. And this means that apart from the kind of a bit boring just particle numbers that we saw in the beginning, we see even more memory of our initial state here, because we really keep this entanglement between those 2 spins here, and in principle could distill it. Okay, another way to look at this would be to keep the strong disorder. So we only look at the many-body localized phase now, and we have this 3 by 7 array. So it's comparably bigger system, and we place an extra excitation in the system, which is further and further away. So if we go from this greenish to the dark blue, we place our extra excitation in the system, basically another particle with which those 2 can interact, further and further away. And what you see is if this is really far away, basically nothing happens. And as the extra particle gets closer and closer, you see that your logarithmic negativity, which is shown here on the left, decays more. And your coherent information even goes below 0, which basically means that your lower bound for your distillable entanglement is below 0, which basically is a very useless bound. So this means that you cannot you have no guarantee that you will be able to distill any entanglement from this state anymore. Okay, so with this, I would like to thank you for your attention.
All right, thank you. Thanks, Annabelle, for a great talk. So let's see, for the people watching, you can ask questions at any time. We'll transfer them to Annabelle. So I'll start in the meantime. So I actually had a question about the tau bit picture, which I mean, something that I kind of missed from the explanation. I mean, it was really good because it's something that I never understand. But so here, I mean, when you're talking about these measurements that you do to probe the many-body localization, so you need to know what these tau operators are. Is that correct or no?
Well, so basically we assume that they are very close to the actual spins.
Oh, okay.
And what we do then is we really only manipulate the actual spins. So we don't really have, so it would be pretty cool to know what the tau bits are. And there are people who came up with protocols to really, I mean, once you know your unitary transformations you can generate your tau bits and then you know what they are. But for what I talked about, we basically assume that the taus are very close to the original spins, and then all we do is always manipulate the actual spins.
Okay, and so is there? I see. Okay, and is there a systematic way to construct them? Unless in theory, I mean, suppose if you don't, even if you don't care about how to measure this particular probe, is there a a systematic way to construct these tau operators?
Yeah, I think there are protocols to do so, but it's a bit cumbersome. So basically what you want to do is you want to diagonalize your Hamiltonian, and then you want to find the representation in which you are closest to your SIs in the end, or like your sigma I's in the end. So there are some protocols to do it, but it's a bit nasty. And as far as I know, you basically need to diagonalize your Hamiltonian in the end.
Okay, cool, thanks.
Can I also ask a very minor question? Yes, so one of the proxies you used for entanglement entropy was the configurational correlation, but I kind of missed how this was defined. Could you elaborate?
Oh yeah, I didn't.
Oh
yeah, I didn't put this here. So basically, let's see. I think I don't have any definition about this on the slides. Let's see. But so the number entropy is kind of easier, right? Because there you take your system. In this case, I think they had 8 sites or so. You cut it in half. So you look at 1/2 of your system. And then you do, in this quantum gas microscopes, you do many realizations. And so you repeat the same experiment again and again, and then you count how often which particle number occurs in half of your system. And the configurational correlator is similar, but well, you also cut your system in half, and then you basically have to look at how often which configuration appears. So you basically look at each particle number subsector separately. So from this you get how likely is it to have, I don't know, 5 particles in my half of the system. And then for those 5 particles, there are, I don't know how many ways to distribute those 5 particles on your 4 sides. And this way you can define this configurational correlator by just measuring particle numbers.
Okay, thanks.
And but basically, so the thing is, we know that the entire phenomenon entanglement entropy consists of the number entropy, so this guy here, and the configurational entropy. And in this paper here, so this is this paper, they cannot access really this configurational entropy, But what they show numerically, really by just doing exact generalization and comparing, is that this configurational correlator behaves exactly the same way as the configurational entropy would do.
Okay, thanks.
Right. Well, yeah, it looks like we have a shy audience today, so I guess there are no more questions. That concludes the seminar for today. Thank you, Annabelle, again for a great, very instructive
Thanks for having me.
Sure. And I'll just like to announce, next week, the talk that we have next week. We'll have next Thursday, Leonard Davilo from Bielefeld University, and he'll be talking about typicality approach to perturb quantum many-body relaxation. So we look forward to seeing you there. Have a good week.